Notes 3.5, we're starting to get into some higher degree polynomials. We had worked with linear, which is x. We worked with quadratic, which is x squared. We're next going to work with cubic functions, which is an x to the third equation. Quartic function is an x to the fourth equation, and you can keep going with them. Basically, a polynomial, okay, so if I have like x to the fourth plus x to the third, this is called a binomial because it has two terms. If I just had one term, it was a monomial. If it has three terms, then it's a trinomial. Basically, poly just means many terms. Okay, so a monomial, binomial, trinomial, all those are types of polynomials, and it could get bigger than that too. Our leading coefficient is the number in front of the highest exponent. Okay, so this would be like a 1 x to the fourth. The leading coefficient is a 1. Okay, our domain of these types of functions is from negative infinity to positive infinity, is all real numbers, and they are continuous. They're smooth and continuous. So yes, they are continuous functions as well. Okay, so we have some different turning points. If you notice here, it goes from going up to coming down. That's called a turning point. Okay, where it changes from increasing to decreasing. So decreasing to increasing is another turning point, and from increasing to decreasing is another turning point. Okay. Basically, we have local maximum and minimums, and we have absolute maximum and minimums. Okay, the absolute is overall, out of all of them, the highest or lowest. Okay, so this point right here would be a local max. This point here would be a local, and so local is a kind of overall term, and an absolute max, okay, because it's the absolute max that it goes to, right? Okay, that's the highest point. This is a local min, and there is no absolute minimum because it keeps going down through infinity, so it's going to keep going down, down, down. I guess you could say the absolute minimum would be negative infinity, but we can just say there's no absolute. Okay, so this one here, since it goes down, 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 and up, 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 there's no absolute max or min. Okay, but there is a local max and a local min. Okay, so if you look at these down here, okay, so they keep going, 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 so there's no absolute max. Okay, and this point here would be a local max. This point here is a little lower than this one, so this is a local min. This point here is a little lower, so it's a local and an absolute min. Okay, this one here, once again, keeps going up and keeps going down, so there's no absolute maximums or minimums. This would be a local min, and this is a local max. Okay, so the idea of absolute and local maximum and minimums. Okay, identify the local extreme points of f. Okay, so here's f of x. We want the local, so local would be the point AB and the point CD and the point EH. So we have three of them. Identify the local extremes of G. So G, we have JK and we have MN. Describe the absolutes. Okay, so in F, okay, there is no absolute max, okay, because it keeps going and going, okay, and the absolute min would be the point EH. G, no. Okay, now to the next point here. The number of turning points, the number of x-intercepts, and the end behavior. Okay, those are our three topics here. So the number of turning points. If this is an x to the fourth equation, there's going to be, okay, if x to the fourth, at most, there's going to be 3 turning points. I'll do TP, turning points. Okay? So if I'm thinking about this, there's 1 turning point, 2 turning points, 3 turning points. At most, if you have any kind of x to the 4th equation, you're going to have at most 3 turning points. If it's x to the 6th, you're going to have at most 5 turning points. If it's x to the 3rd, you're going to have at most 2 turning points. X to the 7th, at most 6 turning points. Okay, so that's the idea of the turning points. The number of x-intercepts. Okay, if it's x to the 4th, you're going to have at most 4 solutions, right? So if you think about 1, 2, 3, 4, and if these just keep going down, you're not going to get 4. So you're going to have at most 4 x-intercepts and 6 x-intercepts. And if it's x to the 3rd, you have 3 x-intercepts and 7 x-intercepts. Okay, and remember, x-intercepts are our solutions, right? So if I see an x to the 4th equation, I'm going to have 4 answers. Now, they may be real answers, or remember how we did it back with quadratics, right? If it doesn't touch your x-intercept, it just means that they're going to be imaginary. But there are going to be 4 solutions if it's an x to the 4th equation. There's going to be 6 solutions if it's an x to the 6th equation. Okay? They're not all unique. Some could repeat each other, right? So remember we had a graph that looked like this. Okay? So technically this is an x squared. There should be 2 answers, right? Here there'd be 2 imaginary answers. Here there'd be 2 real answers. This just makes there's 1 answer, but it's a double 0, right? Remember how that counted as 2 answers. So it's not unique, but it kind of repeats itself. Okay? The next idea is end behavior. So what happens at the end of the graph? Okay, now you can get a graph on Desmos if you want to. The graph would look, I don't know, something like this. Okay. The end behavior. So we have to think as x goes to infinity. So if you think about our x axis here, right? We have 0, we have 1, we have 2, we have 3, we have 4, we have 5, right? And -1, -2, -3, -4, -5. As I go this direction, my x's go to negative infinity. And as I go this direction, they go to positive infinity. So what's happening to my y's, right? My outputs as it goes to, okay? So as x goes to positive infinity this direction, what's happening to my y's? My y's are getting bigger and bigger and bigger and bigger and bigger, right? And they're heading all the way up through infinity. And as I go negative infinity, right, on my x, as I go left, my graph is going up, once again, to positive infinity. Okay? Okay, so negative x to the 6th. Okay, if you would graph it, it'll look something like this. Okay, so we're going to start with our end behavior as x approaches infinity, and as x approaches negative infinity, what's happening to my y or my f of x? Okay, so as x goes to infinity, which means to the right, as I go this direction, it's going, my y's are getting less, 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 going down, down, down. So that would be to negative infinity. And as my x approaches negative infinity, which is this direction, my y's are getting less, 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 which would be to negative infinity. Okay. Now, x to the 3rd, okay, so we think there's going to be hitting it at most 3 times and 2 turning points. But anyway, our graph looks something like this. So kind of a turning point here and a turning point there. Okay. So once again, as x goes to infinity and as x goes to negative infinity is how we set it up. What happens to f of x? What happens to the y? Okay. So as I go to the right, as the x's get bigger, the y's are also getting bigger. And as I go left to negative infinity, my y's are getting smaller. Okay. The next graph here looks something like this. Really, in these type of problems, we're not worrying about what's happening in the middle. We're talking about its end behavior. Okay. So as x approaches infinity, as x approaches negative infinity, what's happening to the y's? What's happening to my f of x? Okay. So as x goes to infinity, which is this direction, it's going down, so the y's are getting less. And as x goes to negative infinity, my y's are increasing, going up to positive infinity. So what I want you to do is kind of think about this. Thinking about our leading, our highest exponent here, if it's even, what are you noticing? If it's odd, what are you noticing? Okay, in class I would have you stand up and do hand motions with me, but basically if it's even, they're both going to go up or they're both going to go down. Okay, so I want you to be able to think about this end behavior without having to put it into Desmos. Okay, so if it's even and it's positive, it's opening up, up, and if it's even and it's negative, it's going down, down. Sort of the same idea when we did x squared, right? X squared opened up, up. Negative x squared was a parabola that opened down. Okay. Now, if it's an odd, if your highest exponent is an odd number, it's either going to be, like if it's positive, it's thinking about overall it's a positive slope, right? So it's kind of going up. Okay. But if it's negative, we're going to have kind of an overall negative slope to it. Okay, you can see how it's going down. So I want you to think about what those look like and what the end behavior is going to look like. Okay. Okay, so the next one's here. For right now, go ahead and think about what this looks like. Okay, so it's going to have how many turning points to it? At most 5. It's going to have, what's the end behavior going to look like? Okay, so it's odd and it's positive. So I know it's going to look like this, right? Okay, as far as the middle stuff, we don't really know right now, but you can go in Desmos. Okay, so now you can go to Desmos and graph it, and it'll look something like this. Okay, so the domain, okay, it goes, this will keep going and keep going, so it keeps going all directions. It's going to be all real numbers, or we write it as negative infinity to positive infinity. The range also, the y's keep increasing and the y's keep decreasing, so that's also all real numbers, or interval notation here. And the local extreme points, you can find those in Desmos very easily by just clicking there, and that point is negative 2.019 and 10.01. And this point down here was 0.408 and negative 4.243. Okay, and if you want to find the x-intercepts, once again you can use Desmos for that. That x-intercept is negative 2.518. This one right here is negative 1, and this one right here is 1.141. Okay, now notice we only get 3 answers here, and it's an x to the 5th equation. So what happens to the other 2, right? If it's x to the 5th, we should have 2 answers. So we don't have any double zeros where it just comes down and barely touches. That means, excuse me, that there's going to be 2 others, 2 imaginary answers. And in the future, we're going to talk about how we find those. Okay, so we'll find those in a little while. Other sections, not today's. Okay, here's another one. Okay, it's a positive x to the 4th. So think about what your end behavior is going to look like. Okay, you know it's going to be up, up, right? Okay, positive x squared. And if you would graph this, it would look in Desmos, I encourage you to do that, it would look something like this. Okay, so by looking at this, our domain, it's going to keep going this way, and it's going to keep going this way. So all real numbers, or negative infinity to positive infinity. The range, okay. Now the range, it's going to keep going up, right? So the top is going to be infinity, but the bottom, the lowest number, we got to find what these lowest points are. And this point right here actually goes down lower than this point here. And that point is at negative 41.6, okay. Okay, so that would be my range. Okay, the local extreme points. Okay, so we have this one right here, which gives me an x of negative 3.43 and negative 41.6. Okay, this point right here was negative 0.38 and 38.3. And then we have this point right here, which is 2.31 and negative 18.64. Okay, so we find those extreme points. Are any of them absolute extremes? Okay, so once again, there's no absolute maximum, but there is an absolute minimum. That would be this point right here. Okay, this is also an absolute minimum. Okay, and our x-intercepts, 1, 2, 3, 4. So we should have 4 solutions. So we have 4 solutions, and all of them are real. So there would be no imaginary ones to find. So we can get them all right here. So it's at negative 4.372, and it's at negative 2. And this point here is 1.372, and the last point is at 3. Okay, so we have no imaginary solutions. Okay, so when you're looking at these graphs, make sure you're looking for at the x-intercepts. So if they say do a comprehensive graph, find the x-intercepts. We didn't really find the y-intercepts, but you could find the y-intercepts pretty easily. Your extreme points and your end behavior. Okay. I'll probably create a I'm going to go on and create a Desmos video with this one.
Okay, so this problem has to do with high temperatures in Daytona Beach. So this is a month. These are the months. So January, February, March, April, May, June, all the way to December, and their average high temperatures. Okay, so notice in January, it's still pretty nice, but then it gets warm, and then it gets colder back towards December. Okay, so this is our data there. Now, in the past, we looked at this data and looked at that and said, yeah, it kind of fits a quadratic pattern, except this little tail at the end, right? So maybe there's another model that fits better. So here's the quadratic model to it that fits. And, okay, so, you know, we've done this ax1 squared plus bx1 plus c. Now here is the cubic one. So ax1 to the third plus bx1 squared plus cx1 plus d. And I also typed in a quartic one, ax1 to the fourth plus bx1 to the third, okay, etc. So you can just kind of expand that out to get your different equations. Let's see which one we think makes the best. So this one has an r squared of 0.9. The closer we can get this to 1 or negative 1, the better. That means the tighter fit. So if you're looking at this one right here, it's not a bad fit. Okay, it's definitely not bad. It's 0.92, almost 0.93. But if you look at this one, does that look like it's a better fit? Does it look like all the points are closer to that? So what happens there is it comes up like this, and it kind of curves over just a little bit right here to get that lip a bit. And we get an r squared of 0.97, which is closer to 1, which is what we want. So this is probably a better match there. Now, your book says something just a tad bit different here with this other one. So if you look here, x to the fourth equation, notice that's the graph that gets there. So not sure why it does it like this. If it makes, I think Desmos has a little constraint on it, which makes it have to be a quartic between these 2 points, which we don't necessarily want it to be a quartic between the 2 points. We want it to be a quartic overall, over everything. So I'm going to show you what is in the book here in just a second as well, and you can see what it does there.
So in the textbook here, they have the quadratic model, which we talked about. They don't show the x to the third model. which would be better yet than that. But this is the x to the fourth they show. So they fits very, very nicely because it fits almost all the points there. And it gives all this equation right there. I'm not sure why Desmos restrains it between here and here to get a quartic, where this kind of is a quartic overall and doesn't really matter what happens over here. Okay, but just being able to realize that there are different models that we can use to get our equation.